Good morning, everyone. I hope everyone's doing well today. My name is Jaswin J. Singh, or JJ Singh. So my topic today is going to be predictive regression modeling using SAS. I thought I was going to be talking about improv comedy, but they changed the subject on me. I'm just kidding. Okay. All right, so everyone here is familiar with regression analysis, I assume, because I imagine some of us have a background in statistics, right? Okay. All right, so it's been used since the early 1800s to find associations between explanatory variables, which are the x's, of course, and the dependent variable y. But usually when you do a traditional empirical analysis, you conclude with saying, okay, we have found an association, a positive or negative association, right? You don't necessarily say that X predicts Y as your conclusion, right? Because prediction is a little bit trickier, and you've probably heard the expression that correlation doesn't mean causation. How many people here have heard of endogeneity? Okay, maybe half the people. My area is empirical corporate finance, and in corporate finance, it's kind of a joke that you can't really avoid endogeneity. One of the assumptions of regression, and well, the most common type of regression, linear regression, is ordinary least squared. One of the assumptions for this kind of thing to work is that you don't have endogeneity, but in corporate finance, we pretty much assume that it's unavoidable. And we always have to say at the end of our papers, well, what do we do to mitigate it? Because that's pretty much all you can do is try to mitigate it. And mitigate means to try to minimize, okay? But anyway, one of the types of endogeneity is reverse causality. So instead of X causing Y, Y is causing X. So maybe your X is Y in the year 2022, and Y is the same variable in the year 2023, then it makes sense that what happened in the previous year is causing what's happening in the next year. That makes perfect sense. But if there are two variables in the same year, it's harder to identify which is causing which. Okay, I'm getting a little bit off topic. Anyway, okay, so the more established predictive regression models available in SAS are flavors of linear and logistic models. Okay, so of course there are numerous kinds of linear models. A logistic model is one in which the dependent variable is either a 1 or a 0, like a yes or no, true or false, that kind of thing. And as Corinne was talking about, there are time series forecasting models. When you access these through base SAS, the time series forecasting models, like she was talking about, you have to go through all the steps of figuring out the ACFs and PACFs. I won't go into detail about what all that is, but it's a bunch of work that you don't have to do with the CAS that she was talking about. But anyway, when you do it in base SAS, you have to go through a bunch of steps to figure out what kind of time series model it is. I will briefly talk about the most basic kinds of time series models, the newer types of regression models are linear and logistic models, falling under the umbrella of machine learning, and machine learning is accessible through SAS via. So I'm just going to put this slide up about how to access the time series analysis and the linear and logistic models through SAS Studio. I thought this might be helpful for people. I don't have the information for accessing the machine learning through SAS via and if that's available through SAS Studio, because I don't have a subscription to that, but I'm not really going to dwell on this slide. Sorry, I'm a little bit nervous. Okay, so let me just explain the most basic models in time series analysis. So time series analysis and forecasting is used quite often for financial time series. So say you are forecasting stock prices or bond prices. The most basic types of time series regression analyses are the autoregressive model, which is called the AR model, and the moving average model. You could have a combination of AR, MA, so an autoregressive moving average model, ARMA. A little bit more complex would be integrated, autoregressive integrated moving average, ARIMA. A variant of the AR model that involves conditional heteroscedasticity. Heteroscedasticity is when the variance is not constant. That's the autoregressive conditional heteroscedasticity model, the ARCH model. Okay, so that's a variant of the AR model. What if it's a variant of the ARMA model with conditional heteroscedasticity? Then it's the generalized autoregressive conditional heteroscedasticity model, the ARCH model, okay? So those are more complex variants of the AR and MA model, and those are often more explanatory. I'm not going to get into any of those. Okay, so just to explain the AR model, it's called an ARP model, ARP in parentheses, okay? So that's basically regressing x at time t, that's your dependent variable, on its own past values, plus a random shock. And random shock is the residual, or the error term, okay, that's epsilon t, the white noise. And the fees here, phi is the Greek variable, or the Greek letter. Okay, so you have a summation here, going from I equals 1 to p. Okay, so the fees are the model's parameters. And so it's basically xt regressed on past values of x, going from xt minus 1 to xt minus p. Okay? So that's the AR model. Okay, in moving average model of order Q, or MAQ model, so this is a process where xt is a linear combination of a sequence of uncorrelated random variables. Mu is the series mean, and the thetas, theta is the Greek letter here, the thetas are the parameter, okay? And here we can see a pattern where there's a lagging going on, one period at a time, starting from, it's a lagging of the epsilon terms, the residual terms, starting from epsilon t all the way back to epsilon t minus q. So it goes epsilon t minus 1, epsilon t minus 2, and it goes all the way back to epsilon t minus q. So we can re-express the equation using what we call a backshift operator or a lag operator, and then that operator we just call B for backshift, and so that just is an operator that operates on B, or sorry, on epsilon. So it just backshifts the epsilon. So this B makes it changes it from epsilon t minus 1. And if you have a B, okay, so this is the first B, and then this will be the next B, and we'll make it epsilon t minus 1, and then the next one will make it epsilon t minus 3, and so on. Okay. So you can see that since this is going all the way to Q, using all of these means that you're taking an average of all the epsilons from time t minus q. And as time goes along, the range from time t to t minus q moves along one step at a time. That's why it's a moving average. See what I mean? Like, let's say it's a 10-day moving average, Q is 10. So the 10 days moves along as each day passes, okay? So a moving average model, in essence, regresses the current value of the series, which is xt, against the current and previous random shocks. Each shock is assumed to be IID. IID means independent and identically distributed. Okay, all right, so that's enough of time series. We don't have to do any more Greek letters and stuff. Okay, so now I want to just talk about the kind of regressions that you're probably all used to, so we're not going to talk about this that much. These are just the most common procs. Okay, so you're probably familiar with the standard bearers here. How many people have used proc reg? Okay. I would say 3/4 of the people here, 2/3 to 3/4. Okay. How many have used proc GLM? Okay, about 2/3. Okay. Proc logistic, how many people? Again, about 2/3. Okay. Yeah, so those are the most common ones. GenMod, probably not as many. Okay. But I don't think I really need to explain anything here. And then there's some comparable ones in VIA. Okay. Okay. So I'm just going to touch on machine learning a little bit. I mean, there's a lot that can be said for machine learning. There's a lot of there's numerous techniques within machine learning, but this is a very quick lecture just about regression, predictive regression modeling. Okay, and even predictive modeling, there's a lot that can be said, but I have very little time, and I've just been told I only have 5 minutes left, so this is going to be rather hurried now. Okay, so I'm just going to explain that The regression part of machine learning is just within the part of machine learning that's under supervised learning. There's three ways in which a machine can learn: supervised, unsupervised, and reinforcement learning. Supervised learning, let's say the selling price of a house is regressed on the numerous features of the house: number of bedrooms, bathrooms, square footage, all that kind of thing. Or let's say a person's loan approval is dependent on numerous things: debt to income ratio, mortgage, loan dollar amount, relative to the value of the house, your credit score, numerous other things, okay? So these kinds of regressions, well, the first one's a linear regression, the second one's a logistic regression. These are kinds of supervised learning where the response data Y is trained on the feature data. We call it supervised because the response data is iteratively trained on the feature data in a manner we call supervised. Okay, so that's supervised learning. It's the most common type of machine learning, and this is the area in which these regression models are found under supervised learning. Unsupervised learning, the data doesn't have labels. An example would be clustering, which is where data is categorized into like groups. Like, let's say you have customers who buy product X, they also tend to buy product Y. But you don't want to market to your customers who bought both product X and Y in the last 6 months, so you cluster and market accordingly. Okay, that's an example of unsupervised learning. Reinforcement learning, the premise there is that you have a computer program that makes an observation, takes an action, and then it receives a reward signal or response as well as further instruction, and it subsequently learns to act in accordance with anticipation of these rewards. Okay? I'll just quickly go over the machine learning workflow from definition of the problem through to the deployment of the predictive solution. So first you collect, clean, and validate the data. Cleaning means deciding how to deal with missing observations, possibly transforming the data into a better form, like maybe taking the natural log of values, like in corporate finance, for example, when we look at firm size, it might be measured in the assets, market cap, or the assets of the company, or the market cap of the company. We might take the log of those values, use log assets or log market cap instead. Okay, then you explore, extract, and engineer the features, decide on your machine learning algorithm. In our case, we're using regressions, so that's kind of a move point. Cross-validate, model design, and hyperparameters. I'll talk about that in a second. And then you deploy and predict. And this is basically saying the same thing. List form. Okay. Okay, so cross-validation, this involves randomly partitioning into, I wrote 2 to 3 because one of them may or may not be required, but there's 3 types of data sets. The biggest one is the training data set. Now, we would like these to be IID, independent and identically distributed, but in practice, they'll be approximately IID, which is fine. And this process is called cross-validation. So the biggest one, which is usually, in my case, I would probably recommend this be 80% of your total number of observations. So this is the data set you use to fit the model's parameters, and you train your data on this using a supervised learning method like linear or logistic regression. Now remember, this is only for machine learning. this is not for your regular statistical linear or logistic regressions, okay? And the goal is to train the data on this data set in order to generate your predictive model such that it will be reliably predictive in a way that you can apply it to other data. For example, a logistic classification, like for credit approval for a loan, with the y variable being a true or false, or 1 or a 0, based on an optimal combination of variables. Okay, now the validation data set, 10 to 20% of the variables. I would say if the training data set is 80% and you need a validation data set, then have this be 10% and have the test data set 10%. If you don't need validation, then have the test data set be 20%. The validation data set is, the last point is, it's not used for a basic OLS linear regression. The reason the validation data set is used is because of the possibility of overfitting. And overfitting can happen if you have too many variables, too many parameters, or too many variables relative to the number of observations. And sometimes in machine learning you can have hundreds of variables, so that's why this can be an issue. So this is another independent data set, that independent unbiased data set that you use for evaluating the performance of the machine learning model. So you take your model from the first step, apply it to the validation data set, and see how it works there, and then you use the final model on the test data set. And if the model fits, if the model fits both the training and the test data sets well, then there's minimal overfitting. But if it fits the training set better than the test set, then there's usually overfitting present. Okay, so just to reiterate, cross-validation of this nature is limited in scope to machine learning. In contrast, statisticians mitigate overfitting by using parsimony, which means they use the fewest number of necessary variables possible in a model. But as I said, machine learning models can use hundreds of variables, so cross-validation using partitioning becomes of paramount importance. Now, finally, recent research has found that the most accurate predictive models appear to be ensemble machine learning techniques, where a number of techniques are used together in combination. And these are often more complex than anything